So 11 AM in CSC module. So yesterday, last class we were discussing about this different indexing techniques, so that access to the database can be faster, right? Because so what we are talking about is a pretty large database which has say tens of thousands of, or to the tune of millions of tuples. So those data cannot be not possible to bring to the main memory for processing. So we need some sort of a indexing which may help in a better access, right? So as we have seen, there are different types of indexes. I'm not going back, and it can be possible to have also multi-level indexing, right? So one level of indexing which points to the actual data records. Then I have another higher in the hierarchy, so that those can be processed much faster speed, right? So one of the popular technique what is extensively used is the B plus tree index file, right? So our alternative to index sequential file. So the problem with the index sequential file that it grows as many overflow blocks are created, right? So what will happen if when we go on delete and insertion or updates in a more if there are more updates, so what will happen? There will be overflow blocks which may need to be reorganized at periodic time, right? Usually maybe a lean period, not in the peak period. So this is a serious challenge, and this B plus T advantage is automatically reorganizes the file with small local changes in the face of the this updates, insertion and deletion. And also reorganize the entire file is not required to maintain the performance, right? So it is more of a localized change can handle that, right? In some cases we need to have a different hierarchy of the things, but most of the cases we can do in the local things, right? There are some sort of a disadvantage which marked as minor disadvantage, that this extra insertion deletion overhead space overhead those are there, but compared to the overall data size and the advantages of this like that less reorganization effort is required compared to index sequential files. So it is one of the what we say de facto indexing approach for this database. There are other variants of B plus. One is the B tree. We'll just see, but B plus is the more predominant. Right? So this is the basic structure of this B plus tree, where you have this index in terms of the tree. We'll see the properties, and at the leaf node, this points to the data records, right? Like here, say anything gold. So whatever in the left of the thing is less than the gold, right? If in the main database, wherever the gold points to the this through the right pointer, right? So sorry, this left pointer points to this gold, and all the other entries on the left of the thing is less than this particular record. Here if you see the same key is repeated, right? Here also gold is there, or here Einstein is there again. Here the Einstein is there, right? So there are some sort of more space requirement is there, right? But nevertheless, we will see that this little space overhead is that may be a little disadvantage, but the type of other advantages it basically overpowers that or overcome that. Right? So this way it is this all the leaf pointers points to the actual data records. Right? So these are the basic property of B plus tree. Like all paths from the root to leaf are on the same length. Right? So all paths from the root to leaf are on the same length. Each node that is not a root or a leaf has a has between n by 2, that is ceiling of n by 2, and n children. So 6 node means 3 to 6 children, right? Which are neither the leaf node or the root node, right? A leaf node has between n minus 1 by 2 to n minus 1 number of values. Special cases, if the root is not a leaf, it has at least 2 children. Right? If the root is a leaf, that is, there are no other nodes in the tree, only the root node, it can have 0 to n minus 1 values. Right? These are the other special cases or boundary cases. Right? So typically, a node looks like a key with a pointer, key and the pointer. So K1, K2, Kn minus 1. So pointers we are having P1, P2 up to Pn. So Ki is the search key value. Pi is the pointers to children, for non-leaf nodes, or pointers to the records for or buckets of records, right, for leaf nodes. Okay. So the search key is in order. Right, K1 is less than K2 is less than K3, as we have seen that the search key, like the name like Einstein is, I think, less than gold and like this, right? So initially assume no duplicate keys, but it addresses duplicate keys, what we'll see, right? So as of now, there is no duplicate key. So there is only one occurrence of the key is there. So other properties, like for I equal to 1 to n minus 1, pointer Pi points to a file record which with the search key value Ki. Right. So if Li, Lj are the leaf nodes and I is less than j, Li's search key values are less than that of the less than equal to the Lj search key value. Right? And Pn points to the next leaf of the search key order. Right? So on the P or that so-called left pointer is in the points to the previous thing, and the Pn or the right pointer is the next key in the order. So here, as we see that this Brenti and Calipari and Quick, and it points to the next key of the node of the next to the tree. Right? So non-leaf nodes form a multi-level sparse index on the leaf nodes. For non-leaf node with m pointers, so all the search key in the subtree to which Pi points are less than the K1. Right? Here what we see that whatever all the search key in the subtree to which, say, this Calipari left of these points is less than the Calipari. So for 2 is less than equal to I less than equal to n minus 1, all the search keys in the subtree to which the Pi points have values greater than or equal to Ki minus 1 and less than Ki. So all the search keys in the subtree to which Pn points have values greater than or equal to Kn minus 1. So whatever we have seen, it is just on writing on the on a textual fashion. So again, we have this K1 to Kn minus 1 keys and Pi to Pn pointers. So example of B plus tree. So this is another example where this root and the leaf are there, right, where n equal to 6. So the leaf has a thing to 3 to 5, like as we have seen, right, n minus 1 by 2 float to n minus 1. So non-leaf nodes other than the root can have 3 to 6. Right? Root have at least 2 children. Now, if we query on this tree, so we see that we where the from the leaf node, like we do other in case of other trees, and then if it is greater than Mozart, then fall back to here and then search on here if it is greater than, in this case, Srinivas, and then goes to this particular pointer, and then if these are the leaf nodes, then it goes to that particular points to the particular record. So C is root, while C is not in the leaf node. Let I be the list value such that V is less than Ki. Right? If no such exists, C is the not null pointer in so C equal to the last not null pointer in C. Else if V equal to Ki, set C equal to Pi plus 1 and C equal to Pi. So it goes on going to the next level. So let I be the list value such that Ki equal to V. If there are such a value, follow the pointer Pi in the desired record. Else no record with the such key value K exists. Right? So this way the this search or searching a file will go on. So in this case, suppose we are going to look at the any of the node like Calipari or Einstein. So we go to this Calipari and see that where it points to, and from there we basically points to the actual record in the database. So if there are k search key values in the file, the height of the tree is not more than log n by 2 k, right? So in other sense, if there are something 1 million data, so typically we have 4 node to access. Like if same thing you want to do with a binary tree with 1 million data, so there may be around 20 nodes to access. So what we see that we if there is say take some in 1 millisecond, so we have a advantage costing around say 20 milliseconds here, whereas there we have typically 4 milliseconds to look into the things, right? So it has a definite advantage while we look at the when we even with other type of tree or binary type of things, because again as we are looking for a large set of records where which has a millions of records or tuples which need to be accessed. So update on the B plus tree. So one, if we look for the insertion, find the leaf node in which the search key value would appear. If the search key value is already present in the leaf node, add the record to the file, right? And if the if necessary, add a pointer to the bucket, right? So if it is instead of the pointing to the particular record, it can be added to a bucket. If the search key value is not present, then add the record to the main file and create a bucket if necessary. If there is a room to the leaf node, insert the key value point. Otherwise, you need to split the node. Let us see with the example. So here, say here the split is not there. Okay, we'll come step by step. So splitting a node, take n, because my basically every node has the n by 2 of this ceiling to n number of pointers, right? N number of pointers which it can accommodate, right? So you take in search key value and pointer pairs, including one being inserted in the sorted order. Place first n by 2 in the original node and rest in the new node. If there is a sorted, if there is a split is required. Let the new node P and let K be the least key value in P. Insert KP in the parent of the node being split. If the parent is full, split it and propagate the split further. There is further split it further up. Okay. So in doing so, you go on propagating that split things. So if these things happens, then you may then the overall what we say update, it may not be very much local. It propagates to the higher level. So there are some of the cases, but what we will see that this propagation, if it is a large tree, if the propagation is not very large, then also we save on the that overall churning of the whole index file. So splitting up nodes proceeds upward till a node that is not full is found. Right. In the worst case, the root may need to be split, and the height of the tree is increased by 1. Right. Result of splitting node containing Brandy, Calipari, and Crick inserting Adams will like this. Right. So it was. Here the insertion was there. So this was, if we see the tree, and then if there is the insertion of the Adams, so it is split into 2 nodes, right? So insert entry this Calipari pointer to the new node into the parent node. Okay. So this is insert before Lamport is inserted. So where the Lamport is inserted, so where if we see the Lamport is inserted. Okay, so what we have is Adams, Branty, Calipari, Crick, Einstein, Elsaid, Gold, Katz, etc., right? Now the Lamport, when the Lamport is inserted, so Lamport it follows this, then come here and then hit this particular it will come here that in the gold, then it is the Kim. So if you want to insert, then what will happen? It will basically split into 2. So it is gold and Katz, and Kim and Lamport is in the thing, because this basically this node is full. There is no empty thing is there. So it is split into 4, and this, in order to address that, the Kim is brought upward, this key value, and this need a split again in this Calipari Einstein gold that needs a reorganization of the things. So Calipari Einstein will point to the things, and Kim will become a new node in this particular level 2, right? So it is not only split here, the split is propagated at the upward, right? And this particular root node is now again reorganized with the gold Mozart. Initially it was only Mozart, and then again reorganized into the thing. So what we see that if some of the split will go on propagating into the upper things, but something which could have been inserted here may not require anything, or if there is a insertion out here will not require, or inserted WU if it was not there U, so it could have been straightforward. So if we look at the insert in the thing, split a non-leaf node when the insert KP into the already full internal node, copy A into a in-memory area M with a space n plus 1 pointers and n key. That means you create a provision with the things where actually initially you are taking that there may be a requirement of more data. Insert KP into M, right, and copy this P1 K1 to Kn minus 1 n by 2 by minus 1 to Pn from m back to the n pointers to the node n, and copy the rest from m to the newly allocated node, right? Insert this kn minus 2n into the parent n, right? So the full pseudocode is available in the book. If you refer to that soft copy of the book, the full this code is available. So once we delete, the same thing goes on. If it falls below the that minimum node count of the things, there will be a merging. Right? In this case, Srinivasan is deleted, so that node need to be again reorganized. Right? So into a form. So what we see here, that even the root node key value also changes, right? So that overall reorganization. But if you can see that some of the things, like especially the leaf node, a major portion of the leaf node is unaffected by the things. Right? So that means it is propagated based on the that effect, that local effect of that particular item being deleted or inserted. This can be, this is only for a few data, but if the key is pretty large or the number of records is the tune of millions, then it has a definitely has a tangible effect on this overall reorganization of the index structure. So here, this Srinivasan deletion merging of under full leaves. Right? So it will, in this case, Mozart, Singh, and UE is merged. So what we can see that there is that the key appears in multiple levels. So it adds to some of the more memory. It takes more space in the overall key structure. Only thing is that as we are only storing as the indexing, so this overall load may not be that large. What it gives in a advantage of overall searching, local reorganization during any update. Or comparing to the overall data load in the backend database. So again, deletion of Singh and U from the result of the previous example will again look for some go for some reorganizations. So leaf containing Singh and U become underfull, borrowed a value Kim from its left siblings, and search key value in the parent changes as a result. Okay, so before and after deletion of the gold from the earlier example, right? So if we delete the gold, that means which is the key in the root, right? So overall the root need to be reorganized. So it rather in this case the level of the key is reduced by 1. So the node with the gold and cats become underfull and was merged with its sibling, right? And the parent node becomes underfull. It is merged with its siblings, and values separating the two nodes at the parent is pulled down when the merging is done. Right? So in case of insertion, we have seen that there may be a split and there may be an increase in the level. And if there is a deletion, there may be scenarios where if the particular node is underfull, then there may be merge of the siblings, and overall the level of the tree may change or may be reduced. Right? So here, if we delete the gold, this become a underfull, so it needs reorganization. So it is appropriately merged with his this scheme and Mozart, right? And as a result, there is a change in the parent, which again becomes underfull and need to be merged. And as a result, what we see, the level of the tree may reduce. So root then has only one child, and is deleted, and this overall level decreases. So find the record to be deleted and remove it from the main file or main file and the bucket if present, if there is any bucket as such. Right? Remove the search key value and pointer from the leaf node if there is no bucket or if the bucket has become empty. Right? So if the node has too few entries due to the removal, and the entries in the node and the siblings fit into a single node, then the merge the siblings, as we have seen in the last case. So insert all the search key values in the two nodes into a single node, right? Like in the last case, what we have seen that this this cat, scheme, and Mozart are now pushed into single node rather in the upper layer also. So delete the pair ki minus 1 pi, where pi points to the deleted nodes from its parent, and recursively use the above procedure so that it go on propagating in the hierarchy. So again, B plus tree delete or updates on delete. That is, otherwise, if the node has too few entries due to the removal, but the entries in the node and a sibling do not fit into a single node, then redistribute the pointers. Right? So redistribute the pointers between the node and the sibling such that both have more than the minimum entry of the entries. Right? So both should satisfy this n by 2 ceiling. So the node deletion may cascade upward till a node which has n by 2 or more pointers are found. If the root node has only one pointer after deletion, it is deleted and the sole child becomes the root of the node. Okay, like what we have seen that in the other case, right? So it is deleted and then the sole child becomes the root of the node. There is a variant, rather there is another tree what we have, that B tree index file similar to B plus tree, but B tree allows search key values appear only once. So the overall working may be similar, but in B tree we have the search key values will appear only once. Eliminates the redundant storage of search key values. Right? In the B plus tree what we have seen, there are a lot of redundant storage in the search key values, but in the B tree it appears only one. So generalized B tree is that P1, K1, P2 up to K1 up to Kn minus 1 and P1 to Pn, and non-lead node pointers Bi are the bucket or the file records of the things, right? So it points to the this files or the bucket if there, if the bucket is there, right? So this is the same way, right? So what we have, suppose now say Einstein. So one is that coming to these things, and it also points to this particular record. So where the Einstein record, Katz records, and things like that for the this node. So same thing if we have a B plus tree, so its structure is like this as we have seen, right? So what we say, there is a repetition of some of the keys, right? Like Einstein or Gold or Mozart or Srinivasan, whatever the non-leaf nodes are there, there is a repetition. Here there is no repetition of the value. So as such, as per the index is concerned, the space may be more utilized in a better way. So advantage of B tree indices may use less tree nodes than a corresponding B plus tree, right? Here the number of nodes are less, right? Sometimes possible to find search key value before reaching the leaf node. Right? So you can at a higher level and go to that particular files, a particular record or the bucket. The disadvantage of B plus tree is that only small fraction of the search key values are found early. Right? So non-leaf nodes are larger, so fan out is reduced. Thus, B tree typically have greater depth than the corresponding B plus tree, right? For a large number of if there are large number of records. So insertion deletion are more complicated than in B plus tree. Right? So implementation is harder than B plus tree. So considering all those, though it is has some advantage of having less space requirement due to not repeatability. So B plus tree is considered to be more efficient in case of large data record, if there are large number of records, and being the de facto standard of this database. There are possible of multi-key accesses while multiple, like a select ID from instructor where department equal to finance and salary equal to 80,000. Possible strategies for processing query using can be: one is use index on the department name and find the instructor with the department have name finance and test for salary equal to 80,000, or you index on the salary and then test for department name, or use index department name index to find the pointers to all records pertaining to finance department, and similarly use index on salary, take the intersection of both the sets of the pointers. So it can be if there are multiple key, so there can be different type of possible approaches, right? This is a brief about the overall indexing strategy. Next, we'll look into the hashing, that is of thing. So what we'll do, rather we'll stop here today. So this we'll look into the hashing in the next class, like that with the this different hash function and hash file organization. So there is static hashing and what are the other approaches of dynamic hashing and things that we will see in the next class. So what we will do, let us stop here and you please log into your Moodle account by 11 a.m. Many of your friends might not have joined this, is not available here. So you please inform other also. So at 11 a.m. We'll start that quiz in Moodle, CSE Moodle. Okay. Thank you.